All right, day number 2 of parametric and complex. We're going to introduce complex numbers. You may recall I is equal to the square root of -1. Therefore, I squared is equal to -1. I cubed is equal to I squared times I, which is -I, and I to the 4th is I squared times I squared. Alright, so these right here are our 4 that cycle back to us. So example, I to the 38th is going to be I to the 36th times I squared. Alright, so how I would go about just understanding this is I to the 4th 9 times, and that'll be multiplied by -1. So I to the 4th we know is 1. 1 to the 9th is 1 times -1 is -1. Okay, so everything breaks down into 4s. So I would, regardless of the power that you're given, I would just break it down into power of 4s and then leave whatever's left over, which will give you one of the following on the edge of that. All right, so let's move into working with complex numbers here. All right, so a complex number, what is a complex number? It comes in the form x plus iy, where x is the real portion and y is the imaginary portion. Okay, so example here, if I wanted to solve where x squared equaled positive 4x minus 7, what I would want to do is I'd want to get it all onto one side, set it equal to 0, and hope that I can factor. In this case, I cannot factor. Therefore, my next option is to use the quadratic formula. So our quadratic formula is x equals -b plus or minus the square root of what? What goes on the inside? b squared minus 4ac. Now this red portion is called the discriminant. And what the discriminant says is if b squared minus 4ac is greater than 0, you're going to have 2 real solutions. If b squared minus 4ac is equal to 0, you have 1 real solution. And if b squared minus 4ac is less than 0, you're going to have potentially 2 imaginary solutions. Okay, so this is what we're going to be dealing with here. Imaginary solutions in the form x plus iy. So let's go ahead and do it. Alright, so here we see that a equals 1, b equals -4, and c equals 7. So we go ahead and do a quick calculation. X equals -b plus or minus square root b squared minus 4ac all over 2a. I can see right now our discriminant is going to be negative. Looks like a -12. Okay, and the square root of -12. Let's look at that a little bit more in depth over here. Okay, that negative, right, what I could do is write it as -1 times 12. Square root of -1 times the square root of 12. Square root of -1 we know is I, and the square root of 12 reduces to 2 root 3. So I have plus 2i root 3 over 2. So I've got 2 solutions. Those solutions are 2 plus I root 3 and 2 minus I root 3. So I reduced up here, turning that into a 2 and that into a 1. Alright, so those are our solutions. in this case, to the following polynomial. All right, so that's using quadratic formula to find complex solutions, or in this case, we call them imaginary, but a complex number is imaginary because it has that I attached, but it also has, you know, a real portion attached in that X form at the front here, right? So here's your real portions, and here are your imaginary portions. All right, let's do another problem here. All right, so the real portion in this form here, of course, we already looked at, is X, and the imaginary portion is Y. This is just math language for what is the real portion of the complex number Z. It's X, right? And the imaginary portion of that same complex number is Y. All right, so in this process right here, we're going to divide. It looks like just division, but we're actually going to add, we're going to multiply, and we're actually going to subtract as well along the way. So how in the world would I divide 2 plus I and 3 minus 4I? Here's how the rookie would try to do it, and they would be very wrong, right? They would say minus I over 4. That is incorrect and not allowed algebraically. What we want to do anytime we divide is we want to multiply by what's called the conjugate. We've done this before with conjugates. Conjugates are our friend. We're going to multiply by the conjugate of the bottom, which would be 3 plus 4I. The only thing that changes is the sign in between. So that's going to require me to FOIL on the top, but on the bottom, because those two are conjugates, all I have to do is first last, right? Because those outside and inside terms will cancel. So in the denominator, I get 9 minus 16I squared. Okay, in the numerator, I'm going to FOIL, I get 6 plus 8I plus 3I and plus 4I squared. Okay, so recall anywhere that you see an I squared, we're going to input a negative 1. So really what I have here is 6 plus 8I and 3I will add to 11I. And then I have minus 4. In the denominator, I have 9 minus a negative 16. So I'm going to regroup here, add some like terms. 6 and negative 4 will be a 2. So I have 2 plus 11I over, and then I group these to make that 25. So the complex number I want to split up into this form, and this will be my answer. Here you go. That's the solution to dividing 2 plus I and 3 minus 4I. Much different than the what we thought might be a quick way to do that at the beginning. All right, let's move on to a more abstract example where we'll look at maybe some identities involved. Okay, so here we got a much more loaded problem than the previous one, but what we're going to do is exactly the same as what we did. All right, we're going to multiply top and bottom by the conjugate of the bottom. Conjugate would be cosine of beta minus I sine of beta. So I'm going to multiply top and bottom times that. Be back in a second. All right, so let's go over what I've done here. I FOILed the numerator, got cosine 2 beta cosine beta minus I sine beta cosine 2 beta plus I sine 2 beta cosine beta minus I squared sine 2 beta sine beta. Now, in the denominator, when I do the multiplication of those conjugates, I get cosine squared beta minus I squared sine beta. And just so you're aware, this becomes cosine squared plus sine squared because the I squared being a negative 1 turns into that. So the denominator ends up equaling 1, which is great. Makes things easy. Now the numerator, what I'm going to do is I'm going to group the blue portion and the green portion. Okay, and I'm also going to group the black and the red. So what happens here with the green portion is this minus I squared becomes just a plus 1. So the blue and the green become the following. I get cosine of 2 beta, cosine of beta, plus sine of 2 beta, sine of beta. Okay, and then the second portion, I'm going to pull out a negative I, and I get sine of beta, cosine of 2 beta. Get that directly from right here. And the other portion, since I pulled out a negative I, that'll make this a negative sine of 2 beta, cosine of beta. Okay, now we're going to do a little simplifying here. This right here is cocosine, and because I have a plus in between, that is the cosine of the first angle minus the second angle, right, which would be cosine of beta. All right, over here, I have what would be the sine of the first angle minus the second angle. All right, and that would come out to be sine of negative beta. So what we have in turn is we have cosine of beta minus I times the sine of negative beta. Now there is a way for me to simplify this. This is an odd function, therefore I could take sine of negative beta and make it equal negative sine of beta. So that would negate the negative sign out in front, and so this, all this simplifies to is the following. That's it's pretty awesome. Some extreme identity use there as well, which kind of gets us back into that track of thinking, which is really good for you. All right, let's do a couple homework problems. All right, so you're going to like this after what we just did. I want real to equal real. I want imaginary to equal imaginary. So that means 2x equals 8. That means x equals 4. All right, that means I want 3 to equal 6y. That means y would equal 1/2. That was nice. Okay, in this case, if I want to know what x and y are, I'm going to have to do some foiling. That would be 4 plus 6i plus another 6i plus a 9i squared. Recall I squared is -1. So I would have 4 minus 9 plus 12i. Looks like I'd have -5 plus 12i. I've got my real portion, and I've got my imaginary portion. All right, let's continue. All right, this one, what I would suggest doing, and I'm not going to do it, you're not going to want to use conjugates here. You're going to want to actually use binomial expansion. And recall that binomial expansion uses Pascal's triangle, so I'd have a 1, 3, a 3, and a 1. That would be 1 to the third, I to the 0. And that would be 1 to the second, I to the 1. And it would be 1 to the first, I to the second. And then it would be 1 to the 0, and I to the third. Okay, so you're going to want to do that top and bottom. That would be expansion of the top. Do the same thing for the bottom. Combine like terms, and you'll be able to do a lot more with that. Okay, on this problem, what I would do, you could multiply by the conjugate of the denominator immediately. That's going to cause actually a lot more work. What I would do is multiply both sides by the denominator on the left, giving me I times 1 minus z squared over here, which would be 1 plus z squared is equal to I minus iz squared. Okay, I'm going to bring the z squared on the right over to the left. So I would get the following. I'll bring the 1 over to the right. Okay, I'm going to factor out a z squared. And in turn, then I'm going to divide by said thing. I'm trying to isolate z so I can determine what that would be in terms of a or x, I, and y. These would obviously cancel here, so z squared would equal negative 1 plus I over 1 plus I. Okay, if you're thinking conjugate, you're thinking right. That'd be 1 minus I on top and bottom. Let's see how far you can get with the rest of that. Okay, I foiled the numerator, did my work in the denominator. Looks like I get z squared equals, these two will cancel. Looks like I'll get 2I over 2, which means z squared equals I, which means that z equals plus or minus the square root of I. Kind of a weird answer, but there you go. Okay, this I think this slide I'm going to leave alone, let you work on that one. I'd like to show in number 5 here that z squared equals the following. It's actually a pretty cool identity. So I'm going to take this thing, which is called z, and I'm going to square it. So that means I would have cosine of theta plus I sine of theta times itself. Oops, cosine of theta plus I sine of theta. So if I FOIL that, I get cosine squared theta. Then you'll notice these are both the same, so I'll get 2I sine theta cosine theta. And then I get plus I squared sine squared theta. Okay, so I squared sine squared will become negative I, or excuse me, negative sine squared. So I'm going to take that, I'm going to bring it over here. So I got cosine squared minus sine squared plus this piece right here is really I sine of 2 theta. Right, sine of 2 theta is 2 sine theta cosine theta. So I just got that I that trails along with it. This right here is an identity. It's cosine of 2 theta. And therefore, what I got is what I was looking for. Using identities, using a little bit of multiplication and understanding what I is, right? And when I square it and when I cube it and all that good stuff. All right, that is whatever lesson this was. I don't remember the day, maybe day 5, something like that. No, day 2, using the conjugate and all sorts of arithmetic on those complex numbers. Peace.